In this section, we're going to talk about the topic of surface integrals. Now, back in section 5.2.1, we discussed the idea that a line integral was useful for adding up a quantity over a given curve C. We had this idea that we would accumulate a quantity as we traversed along a path throughout space. And in this section, we're really just going to be trying to extend that idea to adding up a quantity over a surface indicated by Greek letter sigma. And this is what we refer to as a surface integral. So again, this idea of adding up a quantity as we kind of traverse over an entire surface. Now, this idea actually has a lot of really useful applications, like adding up charges across a magnetized surface. Some of you might be aware in physics that if you magnetize certain surfaces, it can send electrons out to like the edge of that surface, and so you might want to gather up all of the charge as you move across the outside of some sort of closed solid. We might be interested in adding up gravitational forces that are acting on some sort of a surface, maybe like in this picture down below. So maybe I can understand how much force there actually is acting from gravity on any given portion here, and also in total. I could be interested in adding up the density across a surface, kind of like finding the density at each individual point and adding that over the course of the surface to get the total surface mass. And another application that we'll actually talk about in a later section is this idea of fluid flow. If I could add up the amount of fluid that flows through sigma, and kind of like the rate at which that happens, I could ultimately add up in total total amount of fluid that flows through sigma in a given time period. So these are all the sorts of things that a surface integral might be able to help us do. But how do we actually construct an integral like this? It's actually a lot easier than we might first expect, and has some classic kind of calculus components in the construction. So let's take a look here. Suppose we have a smooth surface sigma, maybe kind of like this greenish figure that I have here. And we plan to move across this particular surface and add up a quantity that at every given point given by some other function. So note here that the function that I have is not necessarily the same thing as the surface, right? Like the surface and the function are different items. This function here is just telling me how much charge or how much gravitational force or how much density there might be at any given point along the surface. Let's let Q represent the total quantity of what it is we wanted to add, whether that's a total mass or a total amount of charge, whatever that might be, we'll call that Q. So how do we find Q? Well, the story is a pretty standard one. We're going to start by taking this surface and chopping it up into a bunch of patches. Okay, so you can see here I've kind of drawn some lines that are kind of going across the surface in one direction, some that are going across it in another direction, to kind of create this grid over the top here. And we'll suppose that I chop this up into like n different patches. Okay. Now I'm going to consider the kth patch, which is indicated here by this little black square. And when I look at that kth patch, I'm going to do something rather important. Once I have that particular patch, I'm going to choose a representative point. So I'll choose a representative point, and I'll give this point the name P sub k. We'll suppose that it has coordinates of xk star, yk star, and zk star. So the stars again are just there to indicate this is a special point. And this is a special point for this patch. Okay. Now, I need to start figuring out how much of this total quantity is kind of existing over this patch. What is the estimation of Q over this particular portion of the surface? So to help identify this, I'm going to identify a couple other things. I'll say if Q sub k represents the quantity that we're after over this patch, and we'll let delta S sub k represent the surface area of this patch. then I can start to do a couple other things. Okay. So I'll say it would then have to be the case that, well, Q sub k, so this estimation of the quantity that I want, should really just be able to be represented by my function evaluated at my special point. So this f of xk star, yk star, zk star, just being multiplied by that surface area. So again, what I'm doing here is I'm saying, all right, I have this particular point, and if I can say that there's some quantity that's happening at this point, and this is representative across the entire surface, well then I could just imagine saying, well, I have an entire surface worth of this amount to contribute to the quantity. And so I'm taking this quantity that I have and I'm multiplying it by the surface area. That gets me this kind of total quantity for the entire patch. Well, if that gets me the quantity for the entire patch, then it should be the case that Q, the actual quantity, would be roughly equivalent to the sum of just adding up all of these particular approximations. So I could say, like, well, add up all of these different Q sub k's given by my f evaluated at our special point times delta s sub k, and do that starting at patch 1 and going all the way to patch number n. And so we would then also suspect that I could make this approximation better and better and better if I didn't just use n patches, but what if I let the number of patches approach infinity? So I'll say if we let n approach infinity, then we suspect that Q would actually be equal to the limit as n approaches infinity of k goes from 1 to n, and I have f of my special point multiplied here by this delta s sub k. And what I'll notice here is that this actually represents the idea of a double integral. Now, we saw double integrals in the past as often being represented as having two summations. And technically here I would use two summations to kind of traverse both the horizontal and vertical, or kind of the left, right, and front to back movement of these patches across the surface. Here I've kind of just, for simplicity's sake, summarized them in a single summation. But in general, this could be thought of then as being just a double integral over the surface of sigma, where I have my function f of x, y, z just being multiplied by this ds. Notice here this is a d capital S because I'm measuring surface area, and not a lowercase s like we have with line integrals, where we were talking about an amount of arc length. Okay. So this idea here leads us to the following definition. Assuming that f is a continuous function, the surface integral of f over the surface of sigma would be given by this integral. And now, in a classic sort of way, what we end up seeing is that, well, this integral is very difficult to evaluate. We've noted that throughout this chapter, we set up lots of integrals that are difficult to compute. And so after we can see the construction of an integral, we have to go on the hunt to figure out how we can evaluate it. Well, we can see here that one of the ways that we might be able to help with the evaluation is to actually parameterize this surface. We talked about parameterizing surfaces previously, and let's take a look at what the following remark says. If I had a parameterization, an r of uv, and that parameterized the surface sigma, we saw back in section 4.4 that the surface area for this patch, this delta S sub k, that's appearing right back here, could be substituted by the norm of the cross product of the partials of r with respect to u and v. Okay? This, remember, came from the idea that the two vectors that are created by these partials, if I do the cross product and their norm, I find the area of the parallelogram determined by them. And that gave me an approximation for the surface area of the patch. So notice that if I was to sub that in up here instead, it would create a different integral on the other side. And ultimately, here's what I would end up with. I would say that assuming that f is continuous, my surface integral, which we had previously written to look like this, could now be thought of as a double integral where my f function has to be updated in terms of my r of uv. So again, remember this notation is just saying I need to update the x's and y's and z's in terms of the components of this vector function of r. And then at the back, this delta s sub k is going to get replaced with the norm of the cross product of my partials of r multiplied by this dA. Okay. And now, since I'm going to be actually dealing completely here with a integral that's going to be entirely in terms of u's and v's, it should be noted that this dA is actually going to be some combination of du dv, and I'm going to be integrating over some region D that exists in the uv plane. So this would be a way that I could take this difficult integral and actually turn it into something computable. One other final thing to note here before we end this video is that, remember, we can add up lots of different things with our particular function. This function can actually stand for a whole bunch of different types of quantities that we might want to sum up over a surface. However, if it's the case that our function is actually equal to the number 1, then it's actually the case that this integral here would become this integral, or it would just become this integral over here. That is, this function completely drops off, and we actually should recognize that as the surface integral formula that we had in section 4.4. So if I choose the function that I want to add up over the surface as just 1, then what I end up with is just the surface area integral. So it's really nice that this idea, again, plays nicely and works perfectly in conjunction with the ideas we previously discussed about surface area. In the next several videos, we'll take a look at how we actually go back through parameterizing various different kinds of surfaces and get some idea of how exactly we can use a surface integral in practice.